Well, good evening and welcome to Space Oddities. Thank you for joining us on this Tuesday evening. I've got the usual suspects with me this evening. How are you, Daz?
I'm fine, thank you very much.
Good.
Making
And
a
Roger?
move.
Good evening.
Good evening, Roger. And all the way over the other side of the pond, how are you, Lou?
Oh, I'm well, but I forgot how to say it in British. How do you say that?
Tickety-boo, tickety-boo.
Tickety-boo.
I'll just write that in the chat for you, Lou, so you can see how to spell it.
Copy and paste.
Cultural
Copy and paste.
understanding.
There you are. There you go.
Yeah, copy and paste and put it into your lingual checklist and all that. So yeah, how to speak proper England. So,
Or better still, if you've got a professional email signature, add it to your email signature. Lou Mayo, I'm Tickety Boo. There you are. How's that?
I don't think even the universal translator can do that.
Anyway, welcome viewers. We hope you're all okay out there in YouTube land. Hope you all had a good week. We're absolutely delighted to be back with you again. I can't believe it's a whole week since we were last here, but it is. Let me just see who's actually mad enough to turn up tonight. So we got Derek. Hi, Derek. We got Stuart. We got Alan. Jerry. Hi, Jerry. Daz, did you have a chance to send Jerry his prize? Has he had that?
Yeah.
Okay, good.
You know the British postal system.
Yeah.
Hopefully Jerry's got them.
Jerry, in the chat, could you just let us know whether you've actually received your prize yet? Because it has been sent. If not, we'll have to cry, I guess. So there we are. We got
Yes.
Kevin. Hi, Kev. Oh yes, Jerry has received it, Daz. So that's great. Right, on tonight's show, well, we've got a bit of a mixed bag tonight. We've got the usual features from Roger. That is to say, Roger's Guide to the Night Sky at the moment, and of course the Viewers Gallery. I'm going to be talking about China, funnily enough, because that's come up in the news a few times this week for different reasons, not all of them good. And Lou's going to be giving us an update on Voyager 1, because I know everybody is mad to know about Voyager 1, or at least should be. And a bit later on, I'm going to be talking about some new techniques for detecting gravitational waves. New technologies that are being developed to do just that, and I think you'll find that quite fascinating. At least I hope so. So there we are. Let's just do the usual stuff. So let's go over and talk about the Space Oddities merchandise, which you can get at the Space Oddities shop. You can scan this code that's just come up on the screen. It's also just appeared in the chat as a link. And you can buy the Space Oddities t-shirts for £20, including UK postage and packing, and the Space Oddities hoodies, £40, ditto. If you're outside the UK, please add £10 to the total value of your order. And you can browse through all of our summer collection for Space Oddities. I'm sure we'll be doing a new one before too long. There, and we also hope to expand the things that we're doing. We've already sort of more or less given up on the idea of coffee mugs, I'm afraid, because everybody we've approached wants a minimum order of a few hundred. So I don't think that's going to happen, unfortunately. But we will hopefully bring you some other stuff. Michael can't be with us this evening, incidentally. He's at a photography meeting. I think, isn't that what he said, guys? I think he was
something along those lines. Yeah. Some about naked ladies and things like that.
Yeah, inverted commas, glamour photography.
Yeah, glamour.
In his dreams. So there we are. Okay, let's move straight on then with the guy who knows everything about everything, allegedly. Roger, interesting night sky at the moment, or is it still a bit bright?
Still no astronomical darkness, but give it a month and we'll start to see some as the days progress.
Right.
So here we go for the 2nd to the 8th of July, the first full week of July. So we're up to a new moon towards the end of the week. So that's good for anyone who wants to do any photography. Here's the first 2 days of the moon's phases, which were done during the morning, or wee hours of the morning anyway.
Lovely.
And still got some activity on the surface there, but nothing outstanding at the moment. It's getting a bit bare again, I'm afraid. So hopefully we'll get some more excitement as the days progress.
Well, Daz will be doing his normal update about the sun a bit later. So
Yes,
we'll find
he
out
will.
what's been happening.
And although this is set for 11 o'clock at night, we are getting to see glimpses of Mercury and Venus in the evening sky after sunset, although it is still very close to the sun, so it's not really properly visible at the moment, but they will be as the month progresses on to see Mercury and Venus in the evening sky. But we've still got the southern parts of the sky dominated by the summer triangle of Vega, Deneb and Altair, so that's quite good. And we've got Pegasus and that coming up through with the Andromeda Galaxy. But during the morning we can start to see Saturn come up through before sunrise, and maybe Mars as well, and also Jupiter. So that's good. Obviously, Uranus and Neptune are still too small and faint to see as it would be when we do have the sunrise, but they are there. But as you can see, we've got Venus and Mercury getting further and further away from the sun. So obviously through the month, that will become more obvious in the western skies. Comet Obers is still with us at the moment, although it is now under, well, it's coming past Lynx and under Ursa Major at the moment. So it's still a possibility, and it's still quite good on the brightness. It's just above naked eye visibility, but obviously with the darkness lacking in the night sky, we will need a camera or a pair of binoculars to be able to see anything of it. But it's still developing a tail. So hopefully we'll see Sunnishan Atlas through the months, and as we are, ooh, what are you doing?
Sorry.
Uh-oh.
Almost hijacked your presentation.
I've been hijacked.
Sorry, Roger. Do carry on. That's interesting. 1 second. I don't know what's happened there quite. 1 second.
My presentation's gone now.
It has. Okay, not to worry.
Oh dear.
Not quite sure what happened there. But that's very strange. All right. Well, listen. We'll if you get that queued up again, we'll come back to you a little later then, Roger.
So professional.
We didn't even get to the gallery.
No, don't worry. There's time for that yet. Don't worry. Okay. Well, I'll just carry on for the moment then. It's been an interesting week for.
Here we are.
Oh, you got it already. Okay. Right. Okay. Fantastic.
Right. Let me get on with it.
Okay.
Right.
I'm not quite sure what happened there, but
no, I don't know what happened there either. Right. Okay. So we've obviously got planets there, Obers and Sunnishan. So that's slowly getting brighter, but
that is
obviously
slow,
by September it will be a lot brighter by all the forecasts that people are calculating. Right, we've got a few images from Lee, and we've got a few images from Kevin as well. So here we go, and we've got a few of the noctilucent cloud display, which was on the 25th for this one, and this is what we've got.
Look at that.
Quite nice. Fortunately, the clouds were below the line of the noctilucent area, so that was helpful for him to see.
What's the bright object there?
Probably Capella.
Ah, yes, probably.
I would say that was Capella.
Yeah.
If that's in the northwest, then that'll be Capella.
Yeah.
And then there's another one he took on Friday the 28th.
Blimey, you've been busy.
was
Oh,
taking it. Yeah,
That's very
with some
atmospheric,
nice,
isn't it?
with some got
Lovely.
some nice
Cool.
star.
Yeah, beautiful.
Mm,
Lovely.
very nice. And then he managed to try and get some aurora. So he's. I'll just read. So
28.
whilst taking my images, 2 youths decided to investigate what strange red light was on my head. On the hedge, his hedge torch. When they wandered up tentatively, I just said hello, and they ran off scared and shouting the perils of an astrophotographer, I guess. Aha. Perhaps they thought he was an alien. And yeah, he got a bit of a purple glow there and a bit of a green
Yeah.
glow as well.
Yeah.
So that's
Yeah, I'll be
So,
talking about that later.
Yeah, definitely there. Isn't it?
it's definitely
Lovely.
there.
Great.
And then we've got a couple from Kevin. This one is Clavius and the South Pole. And this is a 6-panel mosaic.
Oh, very
Look
nice.
at that.
Very nice, Kev. When I think of Clavius, I automatically think of Clavius Base in 2001: A Space Odyssey.
All right.
That's gorgeous.
Yeah.
Yeah.
You know, I think we're going to, with NASA, I think we're going to have an observing challenge, an amateur observing challenge. It's for South Pole observations in line with Artemis. So
right.
I'll report the details on that. You know.
Oh, yeah, definitely.
Okay.
That sounds good.
And then we've got one of Saturn from Kevin as well. And this was 3 all-nighters in a row to catch Saturn during a period of good seeing. And we've got a 2-degree tilt of the rings. And this is what we've got.
Oh, yes.
Oh, stunning.
That's nice.
That is nice.
The structure in the atmosphere there.
Yeah.
That's
Well
gorgeous.
done.
I'm impressed.
Good.
Yeah,
And that was at
with that
25
very
degrees
thin-
altitude.
Yeah,
Yeah.
with the very thin rings. That's really spectacular.
Mm.
Really.
Well,
is.
you won't see them in March because they'll be edge on.
Exactly, yeah.
But Kevin says they'll also disappear again later in the month. So they'll disappear, reappear briefly, and then disappear again. Obviously, due to the Earth and Saturn's positions on their orbits and the inclination and stuff. So that should be interesting.
They're only about 1 kilometer thick, I think. Right? Something very. They're very thin.
Yeah, they are.
Yeah.
They are.
And oh, there. And some other lunar images from me, which was a few days ago. Which was
Lovely.
quite nice.
Can I just say thank you to Gerard for the £5
super chat?
Thank you very much, Gerard. Much appreciated.
He's very
Thank you,
generous.
Gerald.
Yeah, thank you.
And here's my attempt at some Saturn, but I've done this as a series of images from 2020 to 24 to show you how each year the rings change.
Look
No
at
way.
And it's a big change in only 4 years, isn't it? It's amazing.
Yeah, well, it's 5 years.
Well, 5 years, yeah. But even so, when you consider the orbit of Saturn is, 29.5 years?
Yeah.
It's a big change in 5 years, isn't it?
That's super, Rog. Super.
Yeah. Yeah, you can see how my astrophotography gradually improves over the years, although the one at 2024, which Kevin's is far better. Mine was in very, very poor seeing. So that's my excuse, and I'm sticking to it.
We believe you.
All right, then.
I mean, those 2024 ones, that's virtually edge on, as you said, isn't it?
Yeah.
So you can only just see a little hint at the top.
I think it's meant to be it's going to disappear for a short time early next year, I think, if I remember right.
Yeah, during the
fantastic, Rod.
early part of next year.
Yeah.
Right, so I've got that, but I've got a couple of other bits which I can have to play separately due to the fact that I can't put it into a presentation. Hang on.
Just talk about each other among yourselves. So,
yeah, well, that is a beautiful set of images. It just goes to show what they mean about with like the rings and sort of like the tilt.
Right.
Yeah.
Okay. This is a video that Paul Evans from Astronomy Ireland sent in of what he saw on the coast.
and this is a beautiful video.
Oh,
look
wow.
at that.
Paul,
Whoa.
we're just so jealous.
Gorgeous.
If you're watching, we're so jealous. That is a beautiful video.
Yeah.
Look at that.
Perhaps you can get your face to turn green again, Andy.
Yeah, envy.
Ah, perhaps that's what it is.
Yes.
Perhaps I've got over eager jealousy syndrome or
Yeah.
something.
That is gorgeous. Well done.
Yeah, that is absolutely
I
lovely.
mean, I've had a real rubbish season so far. I mean, we've had nothing. During the day, it's been lovely. Then you go out and you think, oh, maybe. Then all of a sudden, clouds out and you can't see nothing. So I'm just as jealous as you are, Andy. It's I mean, that's so bright as well.
Yeah,
I mean,
absolutely.
it's reflected in
That
the
was-
sea. Yeah,
That was
just
quite
gorgeous.
amazing, wasn't it?
Yeah,
It wasn't
that
it?
was.
Yeah, thanks, Paul, for that. Thank you for letting us use that. That's fantastic.
Right. Okay. And then
Paul, I hope is going to come and sit in with us one evening soon, so he can tell us about it more then.
So stunning.
right. Okay. Right.
By the way, thank you so much for your generosity, viewers. Don't forget that you can support us by buying us a coffee by scanning this code or clicking the link in the chat. You can buy Super Chat, which is a direct donation of whatever amount you like to us, and that's much appreciated. And as always, just a reminder that every single bit of money goes towards keeping Space Oddities on its trajectory through the universe, as it were. So that's the way you can do it. And you know, any support is gratefully appreciated, because as a YouTube channel, we have bills to pay like any other YouTube channel does. So thank you very much for anything that you could spare in these straitened times. Of course, everybody's probably going to be celebrating after the election, so everybody will have a lot more money to throw around. And just remember, when you're buying the bolly to celebrate, you know, just remember us a little bit as well. If you would.
Right.
Yeah.
Okay. So during Saturday last week, just gone, I was up to photograph the International Space Station transiting the moon.
I was going to ask you about that. Did you get it?
Haven't you seen it? Oh, you're in for a treat.
No, I haven't.
Okay. Okay. Oh.
Let me just get rid of the our ugly mugs there. There we are. Oh, hang on, let's come back.
Go back again.
There we are. Hey,
Hang on. Oh, why is it not?
stay gone. It won't stay gone.
Hang on.
Okay.
That's a bit annoying. It's not playing.
Oh,
Eh?
you can easily describe what happened.
Hang on. Hang on a minute. Let me try and see if this one's.
Excuse us, because we have a slight technical issue. Oh,
I don't know. Run by amateurs here.
Yeah. Talking of technical issues, you may remember last week that we had a complete drop of our streaming connection, which meant that we ended up having two videos on YouTube, which I relabeled part 1 and part 2 for last week. Having investigated that with our streaming provider, it was a problem at their end, nothing to do with us, for which they profusely apologise. It happens from time to time because it's technology, and you know I don't expect them to run a 100% functional service 100% of the time. That wouldn't be realistic. All technology has problems occasionally. So we do apologise to our viewers for that last week. Totally beyond our control. But let's just hope it doesn't happen again this week. And so far, touch wood, we seem to be okay. Roger, any joy with that, or shall we move on?
It's obviously not playing ball.
Right.
Which is a shame.
If you can, download it onto your computer, and then go to share screen and run it through the tabs at the top. Sometimes that's how I have to do it sometimes.
Yeah.
If it won't play, because it won't play through screen, not screenshot, download. But you get it running actually on the computer, and then it'll come up as a tab at the top, and you can run it through there. Hopefully, give it a go anyway.
Okay, well, let's move on.
Move on.
China's been in the news a lot this week, and not for very good reasons. And I've got a series of things I want to tell you about with regard to China that have happened recently, and big problems, and some very, very dangerous ones as well. So I've called this China crisis, if you remember them. What happened this week? Well, just imagine you're in a Chinese village, just minding your own business, going about your daily job or whatever you're doing, and this happens to you. A Long March booster falls out of the sky, and obviously very close to a populated area. And this is very, very dangerous because that orange smoke that it's emitting, that's hypergolic fuel. That's hydrazine and a few other nasties. It's incredibly toxic, and a whole cloud of it later enveloped that entire village. So China have made absolutely no comment about it, but they are extremely reckless when it comes to launching their rockets, especially doing it over populated areas. And in fact, this is what happened a bit later in the week as well. It's absolutely crazy what they're doing. So Daz, just for the benefit of our viewers, give them the definition of what a static fire test is.
Basically, is you take the rocket out to the launch stand, and you fill it full of fuel. You bolt it down. So it can't lift off. And then you just do a static fire. It can either be a short test, a full-length flight test. But basically, the rocket sits on the stand and just fires away, and you're testing the engines.
Yeah,
basically, it's what it is, what it does on the tin, what it says on the tin. So, but Andy's going to show us something different.
Yeah. So basically, every rocket that ever lifts off has had a static fire before liftoff. The engines have gone through a final test. And a static fire test is the last test, usually before liftoff, just to make sure that all the engines are working and developing the correct thrust and doing what they should be doing. Now, Daz used a very interesting phrase there. He used the phrase bolt down the rocket. That's kind of important, because if not, what happens is that the rocket takes off accidentally, which is exactly what happened this week in China. And because you're doing a static fire test, you're only testing the engines. These rockets are not filled with fuel, luckily in this case. So they haven't got much fuel. But when this one took off, it didn't get very high out. Well, two things happened. Firstly, they had an engine failure. You can see at one point that the rocket starts emitting huge clouds of black smoke, which indicates an engine has blown up. And then it runs out of fuel, and fuel falls back to Earth. But this was incredibly near a populated area. Anyway, have a look at this. And there's the engine blowing up. And it starts to fall back to Earth because now it's fuel exhausted anyway. Now this is the rocket that's meant to be a rival to the Falcon 9. It's about the same size as the Falcon 9 first stage. It's reusable. This one definitely is not. And there's a huge explosion, and just look at the size of that explosion. And let's see the impact from a different angle. I mean, look how close this was to what looks like a densely populated area. Unbelievable. So the company involved is a Chinese company called Rocket Pioneer. I use the word company advisedly because, as we know, there are no real independent companies in China. Everything's controlled by the government. But they call themselves a private company. They're called Rocket Pioneer. And this was meant to be the rival to the Falcon 9. And apparently what happened, well, I think it's fairly obvious what happened. The clamps that held the rocket down failed. They are controlled by software, and they think the software failed and opened the clamps by mistake. So that's that was so dangerous. You know, we don't know if there've been any deaths. We don't know if that actually fell on anybody. Chinese government have said precisely nothing about it. No comment. We don't know, but I think it will be a miracle if nobody was under that rocket when it came down. So let's hope that.
I mean, as you said, this has happened 2 or 3 times.
Oh, with China, it happened.
With China, because I mean, when you look at that first launch, as you said, you can hear the actual. You can see the one of the actual engines explode, and about 2 or 3 seconds later, you can actually hear the bang where it's gone, and that seems to set off a chain reaction. It seems that the rest of the engines have either gone out or have been destroyed, but there's still flames at the bottom of it. Although there wasn't that much fuel on there, there is still fuel on it when it does come down, because that's what causes the explosion. Hence the big explosion. But also, not only did that have the vertical lift, it also traveled horizontally, and like you said, look how close it is to those that built up area.
I know.
I mean, that could have been totally disastrous. But of course, you say it's their answer to these Falcon 9, and actually, when you see a mock-up of it, it's far too similar to be a coincidence.
Oh no, it's a direct copy of the Falcon 9.
Even with the fairings at the top, it looks.
That goes without saying with China.
Except SpaceX flies.
Yeah, exactly. But a near disaster there. If those engines hadn't failed, I wonder how far it would have gone.
How far it would have
gone, and how far downrange it would have gone. The very stupid idea of having a rocket launch facility inland in the middle of a developed area, it just beggars the mind.
I mean, I think it is actually on the coast, isn't it? But it's sort of like at the bottom of cliffs, isn't it?
No. This is well inland. This is hundreds and hundreds of miles inland.
Oh, okay then.
So extremely dangerous. It's not like Cape Kennedy and Boca Chica launching out over the sea. This launches out over populated areas, and look what can happen. But as I said, the Chinese have made no comment at all. Okay, now let's talk about Chang'e 6. You may remember from last week which was the landing of Chang'e 6 and its precious sample from the far side of the moon. And there's been a few developments about this week. So let's have a look. And there we are. That's the thing on the ground. And then we have some scientists just about to release the canister from the capsule. And there's the canister containing that precious sample afterwards, just about to be opened for the first time. This is the first material from the far side of the moon. China welcomes scientists from all countries to apply to study the samples and share in the benefits. In the spirit of international cooperation, that's Liu Yangfen International Cooperation Office of the China National Space Administration, saying that other countries can apply to look at those samples. The administrator of NASA, Bill Nelson, he's quite in favour of the idea. He said, make it available to the international community just as we will when we start bringing additional samples back. And as we did half a century ago with the samples brought back from the 6 Apollo moon landings, it's very positive about this idea. But there's one big problem. And there's a problem. you see there's this piece of legislation in the United States called the Wolf Amendment. And the Wolf Amendment actually prohibits the use of government funds by NASA for bilateral cooperation with China or its agencies without authorization from Congress or the FBI. Neither Congress or the FBI have given NASA permission to apply to look at the sample. Bill Nelson, unbelievably, came back immediately and said, well, China's not invited us to study the samples. So there, and the Chinese came back and said, nonsense, I'm paraphrasing. We told you that any country is welcome to apply. The problem is your Wolf Amendment does not allow you to. If you're serious about future cooperation, repeal the Wolf Amendment and we'll talk. And that's where we are at the moment, that NASA can't get their hands on the sample because American law doesn't let them. On the good side, initial analysis of the sample from the far side of the moon seems to indicate that it's more lumpy and sticky than the topsoil or the regolith from the near side of the moon, as connected by the Apollo astronauts. And it also has a completely different mineral composition. Now, we're very happy about this, obviously, because what it means is that if the sample had come back from the far side of the moon and it had been identical to the stuff we got from the near side of the moon, that would have been a real anticlimax and had a lot of people scratching their heads. But already the preliminary analysis indicates that the geology of the near side of the moon and the far side of the moon are indeed extremely different. And the question, of course, is why, which we hope that the sample is going to give us some clues to over time. It may mean more missions from different locations on the far side of the moon, of course, because you can't really sum up the geology of that hemisphere just from one location. Ideally, you'd want to sample the regolith from lots of locations. But there you are. What do you think, Lou?
I knew you were going to come to me on this, and I thought, well, geez, I know nothing about this. Well, the moon's history is pretty traumatic. And so as an off-angle strike to the Earth, which we believe that's consistent with the arguments for rotation and angular momentum and conservation of energy and all that, part of the Earth's crust, part of the Earth's mantle went into assembling the moon, which happened rather fast after the collision. So I wonder if, as this material is thrown up, a different composition and all of this, if it's settled in that way. Now, I don't know. I don't know that the scientific community has a strong position on this. But I wonder if that is possible. The mantle composed differently than the crust. Heavier materials would have been ejected at different velocities, all this kind of thing. So, like I was saying earlier before the show, good astronomers can talk about anything they don't know about forever. And so I'm just conjecturing.
Yeah.
Sure.
Yeah, because as we said, we were talking earlier again, and I'll just reiterate something I said last week, but I did leave something out, as I was talking about that it being tidally locked. And like Andy said, was it tidally locked then when it first formed? But when it became tidally locked, if it was still quite malleable, and with a very hot Earth, which would be still hot and malleable because it's a bigger object, it'll be losing its heat a tad slower, that it would be heating that side. And one of the theories is because the near side of the moon stayed more malleable when it was hit by anything. Of course, you had the volcanic magma come up and create these seas and things, or the mare as we call them. But on the far side, the actual far side is a thicker crust, and they think that also that because it cooled slower on the one side, the crust on the far side actually cooled faster and ended up being thicker. But then again, there was also a second theory where that when the moon formed out of the explosive magma, that two moons formed, one a smaller one, in the same orbit, but it was moving slightly faster than the bigger moon, and it finally caught up. And because they were, instead of just smashing into it, it was such a slow rate that it actually smeared itself, being still malleable at the time, just smeared itself on the far side just to give it that thicker crust. It's all speculation, of course, but
Could
hopefully
that account
clouds
for the mysterious object of large mass that they found underneath the surface of the far side? Which,
But isn't
they
that
just,
an iron plate or something they reckon? Is it? I'm not sure. I can't remember
well,
now.
last thing I heard, nobody had actually established exactly what it was. They've got some ideas,
Yeah.
but I don't think.
I know they've done seismic measurements inside, and they've
Hmm.
actually mapped the inner structure, and it's a very funny makeup inside and all that. I mean, I'm not fully aware of it, but you can actually see these images where they look, where as you said, it's thicker, it's more denser, and what's actually going on actually inside. So it was very weird, the images of what's actually inside, but
Sure.
yeah, it's a fascinating subject.
I'll tell you what, mates. I used to work very closely with a guy named Dave Williams. Dave is a planetary scientist and a lunar scientist expert.
Right.
And I will, he kind of bounces between coasts periodically, half the time working at Goddard, half the time at JPL. I will grab him when he's on the East Coast, and I will pull him in, and we will have him on the show, and we'll ask him this question.
That'd be lovely. That'd be fantastic.
Yes, excellent idea.
As well as moon trees. We'll ask him about moon trees too.
Thank you, Lou. Yes, that's a great idea. Absolutely superb. All right. So, what have we got left? Right. Okay. Let's move on now to tonight's feature of gravitational waves, if you like. And just let me get myself set up here, and we'll be ready to go. Now, you may remember that a couple of months ago, I actually presented to you a presentation about gravitational waves. What I'd like to do this evening is actually talk about new ways that have come up of, or will be developed in the near future, of detecting gravitational waves of different types. So let's have a look at this. So beyond LIGO, new ways of detecting gravitational waves. Now, before we start, let's just do a quick revision of what I was talking about last time. So this is LIGO. Hope everybody can see this. It uses laser interferometry, and it was the world's first gravitational wave observatory, but there were actually two LIGOs in the United States, one in Washington State and one in Louisiana. And it consists of two 4-kilometer arms, lasers bouncing up and down those arms. Basically, when a gravitational wave hits the Earth, the size of those arms relative to each other changes, and that can be detected. And it's a very, very tiny measurement to make. It's about 1,000th the width of a proton. So it's a very, very, very tiny measurement. But thanks to the advanced technology at LIGO, we can do it. So the first signals, as you may remember, were detected in 2015, that being the merger of two black holes that took place just over 1 billion years ago. We've also got in Europe, we've got Virgo near Pisa, where the famous Leaning Tower is, of course. The laser interferometry, another laser interferometry gravitational wave observatory, built to more or less the same design. And this works hand in hand with LIGO on observing runs. And the advantage of that, of course, is that you've got observatories separated by vast distances. You can triangulate on the sky with the two LIGOs and Virgo. You can actually triangulate and try and work out where the gravitational wave signal came from on the sky. In Japan, there is the Kagra Observatory, again a laser interferometry observatory. To get away from any potential terrestrial vibration that LIGO and Virgo suffer from, this could be traffic, distant ocean waves, any vibration that could be mistaken for a gravitational wave, as they often are. Then what the Japanese have done, they've put the whole thing underground to isolate it from terrestrial observations. And I'm not quite sure what's going on with CAGRA because it's been offline for a considerable time now, but it is a working gravitational wave observatory. So there are basically 4 observatories using laser interferometry to detect gravitational waves, the 2 LIGOs, Virgo and CAGRA. LIGO India is in the first stages of construction. And of course, Europe is planning its Einstein telescope, which again will be underground. And there's a lot of talk at the moment going on about whether it should be in the Netherlands or whether it should be in Italy. It may end up actually being in both places so that we have 2 observatories. And that's under discussion at the moment. But I want to leave that. I don't want to talk too much about that. You see, all of these observatories, all 4 of them, have a limitation. They can only detect gravitational waves between about 1 and 100 hertz in frequency. That is the problem. But we believe that there are sources of gravitational waves way outside this narrow range that we can actually detect at the moment. And if you remember this from last time, this goes from 100 down to 10 to the minus 16 hertz. So at the top end, there's the sort of range that we can listen to, if you like, at the moment. That being merging black holes, colliding neutron stars. At the top end, maybe even supernovae explosion, although we haven't actually detected any yet. It may just be outside the range of LIGO, Virgo, and CAGRA. Then moving down in frequency from 1 to 10 to the minus 4, we start to see supermassive black holes. We start to see objects that are rotating around supermassive black holes in the centers of galaxies. Also, the LISA spacecraft, which Europe is launching in 2034, I think was the latest estimate, which is going to be, again, a laser interferometry setup, but instead of having arms that are 4 kilometers long like Virgo and LIGO, it's going to have arms that are separated by millions of kilometers because it will be a triangle of 3 spacecraft connected by laser. And that stands to pick up gravitational waves of much lower frequency. But moving down, we've got 10 to the minus 9 to 10 to the minus 7, roughly. We've got the supermassive black holes detected by pulsar timing arrays, which you may remember if you're a regular viewer, we've talked about quite a lot. And late last year, the first results from, I think, 5 different pulsar timing arrays all came to the same conclusion, that there is a background hum of gravitational waves permeating the entire universe. And after much analysis, I think the probability has come down in favor of them originating from co-orbiting supermassive black holes at the center of galaxies. But this discovery of the background hum of gravitational waves in the universe is quite important. Once we go right down to 10 to the 14, 10 to the minus 16, these are gravitational waves that date from the very, very beginning of the universe, from the inflationary period. But we will talk about that in a little while. Now, if we put this whole thing on a vertical scale, we've got the frequency going down vertically. We've got the period of each wave, if you like, how long between waves, and it goes from milliseconds right up at the 10 to the minus 2 to 10 to the minus 10 to the 2 and 10 to the 3 hertz, going right down to a period of millions of years at 10 to the minus 16. So in other words, at 10 to the minus 16 hertz, that means that there's going to be millions of years between each gravitational wave. But that is down at the inflationary period, which I'll talk about in a little while, which hopefully will explain it. Just to zoom in on that a bit more. So the yellow area here is what's currently detectable: binary neutron stars, binary black holes, and possibly supernovae as well, although, as I said, we've yet to detect any. And then at the bottom end, we go right down to 10 to the minus 14 hertz to 10 to the minus 16, extremely low frequency gravitational waves with potentially millions of years between each wave, which is amazing. At that point, we've got inflation, which is not shown on here, so I've added it in. So inflation was this period just after the Big Bang where the universe expanded exponentially by a factor of, trillions in a trillionth of a second. And the idea behind this is that we will be able to detect gravitational waves from that epoch. Now, this is being carried out by the Simons Observatory in Chile. They will be observing at 10 to the minus 14 hertz. And if you can't see what's doing the observing here, there we are. Those three dishes there, those three instruments, will be observing the universe's gravitational waves at very, very low frequencies. Now, what are they looking for? We're talking about the cosmic microwave background, which is the, if you like, the first light of the universe emitted across the universe when the universe had cooled sufficiently for photons not to be immediately reabsorbed by other particles when they're emitted. And this is when the universe switched on in terms of light, basically. Now, this is a map of the cosmic microwave background. The different colors represent different temperatures. And we're talking about millions of degrees difference here in temperatures. But this is what gave rise to the seeds for galaxies and everything that followed. These patterns may look a bit random, but actually they're not. And what the Simons Observatory will be looking at is polarization in this light that is now at microwave wavelengths thanks to the expansion of the universe. Now, there was an experiment a couple of years ago called BICEP, which claimed to have found the Holy Grail. What is the Holy Grail? Well, the idea is that during the inflationary period, there was a particular type of polarization that we can theoretically observe in the cosmic microwave background. And it's called B-mode polarization. And what it looks like is a sort of an S-shaped squiggle of polarization. The direction of polarization forms this sort of an S shape. And these are the relics of gravitational wave signals in the light from the cosmic microwave background. And if we could find that, it would do a few things. Firstly, it would confirm inflation, which up until now has never been 100% confirmed. I'm never going to use the word proved, by the way, because in science you never prove anything. You just get better data until the next bit of data that's better. Anyway, if we can see this mode in the cosmic microwave background, it will indicate strongly that we're on the right track with inflation. And it'll also tell us a huge amount about the universe and those gravitational waves that left this polarization in the light from the cosmic microwave background. Now, the Simons Observatory seems to have gone a bit quiet. They haven't released anything or written anything or publicized anything since COVID. I've actually written to them and said what's going on, but I haven't had a reply yet. So I don't know whether the telescope, which was under construction before COVID has been finished, or if they're doing observing. I don't know. I'll keep you posted of any developments. So let's have a look at that. So this is 10 to the minus 14 hertz. And this is the layer, if you like, of microwave telescopes like the Simons Observatory cosmology experiment. Pulsar timing arrays we've talked about quite often. Just to recap, this is the idea that radio signals from pulsars get delayed when a gravitational wave passes through the universe and stretches space-time, so that the signals take longer to arrive at the Earth than they normally would. And these are some of the dishes involved in, I think there are 5 separate experiments that have been working on this all around the world. They've all come to the same conclusion, as I said, that there's a background hum of gravitational waves in the universe that is probably due to co-orbiting supermassive black holes at the centers of galaxies. But more work needed. And that's 10 to the 6 to 10 to the minus 6 to 10 to the minus 9. And that goes on our scale there, pulsar timing arrays. And we're now into years for detecting these waves, years between waves. And in fact, the experiment or the experiments have been running on this, they've been running for 15 years because they have to be. Otherwise, you only ever catch one wave. So there we are. Now, going right up again, increasing in frequency, 10 minus 1 to 10 minus 3 hertz. It's thought at this frequency there may be a population of black holes that we just haven't seen yet. And the odds are that there is. But there's a new technique for detecting these. And it's called atom interferometry, not laser interferometry, like LIGO and Virgo and Cagra, but atom interferometry. Now, the idea behind this is you take a tube. I've actually taken a beer glass here, but, well, why not, basically? What you do with your tube is that you drop 2 atoms into it. Now, what you do then is that you measure how long it takes light to travel between those 2 atoms by firing a laser beam, and you measure the time interval between the atoms and therefore the distance. And you can measure this incredibly accurately down to femtometers. And the idea behind this is that the atoms then drop and you repeat the experiment. It is a much simplified version, obviously, but you do this thousands of times a second to find out exactly how far apart those atoms are to an incredibly high degree of accuracy. The idea behind this is that when a gravitational wave passes through the tube, the atoms will get ever so slightly farther apart as space-time is stretched and shrinks again as the wave passes through, and this can be measured. And the only problem is it's reckoned to get an accurate result and one that actually works. That tube has got to be about 1 kilometer tall, but they're on the case. And in fact, at the Fermi National Accelerator Lab outside Chicago, they're building a 100-meter tall tube as sort of proof of concept of this whole atomic interferometry, if you like. And we'll have to wait and see how that gets on. It's due for completion in 2027. And that goes on to our scale there at 10 to the minus 1 to 10 to the minus 3 hertz, where it is thought there may be a whole population of black holes that we could see through observing their gravitational waves when they merge, that we can't at the moment because we're not observing at the right frequencies. So this could open up a whole new population of black holes to us, if it works. And then we get on to the toy LIGO. Now, this is interesting. Don't forget, as I said, that the arms at LIGO are 4 kilometers long each. Well, in this one, they're only 1 meter long. And you have 2 arms, each 1 meter, and you have 2 mirrors. And what happens in a vacuum between those 2 mirrors, you have a particle that is actually suspended by a laser beam. It's kept in exactly the same place, and which is known to a very, very high degree of accuracy by a laser beam. And the idea here is that if you have a gravitational wave that passes through the equipment and it resonates with the distance between the mirrors, the laser beam will actually give that particle several small kicks as the gravitational wave passes through it. And so the particle will move, and that can be detected. This is the idea behind it. And this is, not surprisingly, known as desktop interferometry, because it means you can have a gravitational wave detector on a desktop, which sounds crazy. Put me in line. I hope they start selling them at Amazon. I'll buy one. And this is known as a levitated sensor detector. And they've actually built one at Northwestern University at Evanston in Illinois. They're currently doing experiments to see whether it actually works. But it should have a detection frequency around 100 kilohertz. Now, the question is, are there any known objects that produce gravitational waves at 100 kilohertz? Don't forget, 100 hertz is our upper limit at the moment. So this is 1,000 times higher frequency than what we're detecting at the moment. What produces gravitational waves in that range? We don't know. There may be nothing, but there may be something that we've never thought of. So it's worth investigating to see what we see. And that goes in there. Levitated sensor detectors goes in at around the 100 kilohertz mark. Now, the last one, more or less, is a strange one. Bose-Einstein condensates. Now, let me just tell you about Bose-Einstein condensates. They're a very, very strange form of matter. Basically, what you do, you get a cloud of atoms and you cool them down to about a millionth of a degree above absolute zero. And when you do that, the cloud of atoms starts behaving like one enormous atom. It's very, very strange quantum effects going on there, which I don't think anybody truly understands even now, even though we've known about these so-called Bose-Einstein condensates for a very long time. In the quantum world, everything's a bit weird. But this is a type can be used to detect gravitational waves. Now, the idea behind this is you throw some sound waves through this cloud of atoms that are behaving as one giant atom at a millionth of a degree above absolute zero. And then when a gravitational wave passes through the condensate, it changes the properties of the sound waves, which changes how that Bose-Einstein condensate resonates in response to the sound waves. Now, I don't pretend to understand the ins and outs of this, mainly because there's not a lot of information, not a lot of fine detail about this, but it's all to do with using sound waves and Bose-Einstein condensates and resonance to detect changes in space-time when a gravitational wave passes through. So that's the Bose-Einstein condensates. And theoretically, this can detect gravitational waves at up to 100 megahertz. So, going up again. And again, are there any gravitational waves at that incredibly high frequency, 100 megahertz? Don't forget, we're stuck at 100 hertz at the moment. So this is a million times high frequency gravitational waves that we can detect at the moment. Is anything likely to be producing waves of that frequency? Again, we don't know. There could be completely new objects to us out there producing gravitational waves of that frequency. Now, don't forget, when the first gravitational waves were discovered in 2015, it was literally like opening up a completely new window on the universe, a completely new science of gravitational wave astronomy. And whenever we have undergone a revolution like that in astronomy through instrumentation, essentially, think of Galileo lifting the fairly newly invented telescope to the heavens. Look how that changed anything. So whenever we have opened a new window on the universe, like radio astronomy, X-ray astronomy, gamma ray astronomy, all of these different ways of looking at the universe, whenever we've done that, we found things that we never knew existed. And gravitational wave astronomy, I'm sure, will prove to be absolutely no different. There may be strange things out there that we can't even conceive of in the universe that may radiate gravitational waves well outside the range of what we can detect at the moment. So it's going to be an exciting few years while all of these different methods are tried out. Now, let's just actually, let's put that back again. There we are. So let's just have a final look at the gravity spectrum, if you like. We've got that yellow band going across horizontally, which represents what we can see at the moment. And then we've got high frequencies going right up to 100 megahertz or more with Bose-Einstein condensates. Then levitated sensor detectors, slightly lower frequencies. Our ground-based laser interferometers like LIGO and Virgo at the moment. Quantum detectors, atomic interferometers, the laser interferometer space antenna, that's LISA, that's the European one I was talking about, launching in 2034. Then going down, pulsar timing arrays, going right down to microwave telescopes at around 10 to the 14, 10 to the minus 16 hertz, which should be able to detect gravitational waves from the birth of the universe. Now, on a related note, let's talk about the Antikythera mechanism. You may know about this. This is something that was discovered in a shipwreck off the Greek island of Antikythera in 1901. Now, at the time, nobody really knew what it was about or what it was. It dates from around 200 BC. In 1902, it was confirmed that there are gears inside this mechanism, whatever its purpose. And it is actually a hand-powered aurorae of the solar system. The fact that the Greeks were making these in 200 BC is mind-blowing. And it's become an object of great study because the obvious question, how? I mean, you know, the engineering required to build this is absolutely mind-blowing. And this is a look of what it might have looked like inside when it was complete. Obviously, you know, it's been in a shipwreck for 2,000 years, so you wouldn't expect it to be complete. But this is what they think the mechanism looked like inside. And it was used to predict both lunar and solar eclipses years in advance. It was also used to track the 4-year cycle of the original Olympiads as well, they believe. Now, this is a digital reconstruction of what they think the face of it might have looked like. And there are all sorts of scales and rings, and basically it's an aurorae of the solar system that also does eclipse predictions, which is truly, truly amazing. Now, this is an X-ray going through the Antikythera mechanism. So you'll see different layers come in and out of vision as we go through it. And you'll see the sophistication of this entire thing. And you can see the gears and the cogwheels, and the way that it's put together is just frankly astonishing. And this X-ray scan really brings everything out. There is quite a bit of it missing, but there has been enough for archaeologists to establish what it was used for and roughly how it worked. Absolutely amazing. And you can find all sorts of information about the Antikythera mechanism. Now, on it, there's the ring known as the calendar ring. And we know it's a calendar ring because it's got the ancient Greek months engraved on it. 2 of them are here. As you can see, I won't pretend to read Greek, but this is known as the calendar ring. Now, the interesting thing about the calendar ring is that behind that ring, it's got hundreds of tiny holes to calibrate it as it's rotating. But part of that ring is missing, so the total number of holes was not known. Now, some people thought that it was tracking the Egyptian solar calendar, which would mean 365 holes in that ring, 1 for each day of the year. But a lot of archaeologists thought, well, in Greece, the Greek lunar calendar would have been more important to the Greeks. So they suggested that the ring originally had 354 holes, which is 12 lunar cycles. And this went for quite a while without being resolved. Was the calendar ring tracking the Egyptian solar calendar or the Greek lunar calendar? And now it has been resolved, just about, with the help of, and if you're wondering where I've been going with this relating to gravitational waves, now I'm going to tell you. This has been resolved with the help of LIGO. So what on earth is going on here? Well, it turns out that statistical techniques developed at LIGO for the detection of black hole mergers, and it's Bayesian statistics, in case there are any maths or stats freaks out there. Bayesian statistical techniques were applied to the distribution of holes in that calendar ring. And it turned out that there's a 68% statistical probability that the ring did indeed have originally 354 holes. So it actually tracks the Greek lunar calendar and not, as a lot of people thought, the Egyptian solar calendar. But they couldn't have done this without those algorithms developed at LIGO for the detection of black hole mergers and their statistical probabilities out of the signals. Now, I mentioned all this because I just think it's a beautiful story of how 2 complete branches of science can merge. And if you want to read more about this, it's in the July edition of the Horological Journal, which is the official journal of the British Horological Institute. And on the right there, you see the article called An Improved Calendar Ring Hole Count for the Antikythera Mechanism. I do warn you, it gets intensely mathematical. However, if you're into that sort of thing, you might like to look out for that, the Horological Journal for July. And it does, as I said, make an important point that quite often discoveries in one branch of science can turn out to have unthought of applications in another. So I thought there was this nice interplay between gravitational wave detection and ancient Greek aurorae, which I think is absolutely delightful. So there you are. That's it, I think. Is there anything else? No, I think that was it. Okay. So guys, wasn't that amazing? Just having these two branches of science that have coincided.
I do have a question for you, Andy.
Yeah.
I'd see if you came across this in your research. So we have a hard stop in observing the universe at about 380,000 years. Yes.
Yeah.
Where the universe went from opaque, where it was essentially dominated by probably me scattering by electrons,
Yeah.
to transparent.
Mm-hmm.
So that is a hard stop if you're looking at the universe in electromagnetic waves.
Yes.
Is there any, and perhaps I missed this if you said it, I'm sorry, but is there any thought that we could look beyond that wall with gravitational waves?
Oh, absolutely. Because there was no such restriction on the passage of gravitational waves, because gravitational waves are waves in space-time itself. They were not impeded by anything when, as we think with that B-mode polarization in the CMB, they were not impeded. They were completely free to travel the universe. Nothing stopped them. So if you like, if we can detect these gravitational waves from, the very first instance of creation with a small c, they will be our telescope into that distant epoch in a way that nothing else can. So, yeah, absolutely. And we could learn, my gut feeling is that we will be detecting those very soon, because in fact the pulsar timing arrays and their discovery of this background hum, the universe is humming because it's forgotten the words probably. One suggestion was that this was a detection of primeval gravitational waves from the inflationary epoch. But looking at the data, scientists don't think it quite fits. But I reckon we will detect them before too long, and then we will have a direct window into the first moments of the universe. It's that exciting. It's what we've all been waiting for, basically, isn't it? Well, I know I have.
Yeah, that would be fascinating, because I can't really think of, other than the actual moment of the beginning of inflation, what would create the gravitational waves. What would be the mechanics behind them being,
Well, you have to remember that gravitational waves are emitted by anything that accelerates in the universe.
Yeah.
So as the universe started accelerating after the Big Bang, or at the Big Bang, it was inevitable that gravitational waves would be emitted from, if you think of what do we have right in the beginning, the sort of quark gluon plasma. As that accelerated, it generated gravitational waves, and this is where they came from.
Yeah, because I mean, the diagram you showed of the waves in the CMB, they were in several directions, which gave you the smooth shapes. Well, of course, some of the theories is that the major original inflation was smooth.
Yeah, but don't forget what you were looking at there was the polarization, not the actual waves themselves. The polarization. Because if you think about how polarization works, it's aligning. If you think of it in particle terms, it's aligning particles in one particular direction, like you get with Polaroid sunglasses with light.
Yeah.
But there are, an almost infinite number of ways that you could polarize that light. Yes. And this is one that just happens to resemble the letter S between particles or between waves.
Sorry, I must admit, actually, I couldn't see the S. But there you go. That was me. I thought it was one of those magic things. I was squinting my eyes and everything. But
Okay. Okay.
yeah, right. Cheers,
Right.
Lou. Thanks a lot, Lou.
No. Right. Lou's got to say goodbye now because he has to go to a doctor's appointment.
Yes,
Yeah.
and we will resolve the status of Voyager next week. So stay
Okay.
tuned.
All right. Well, good luck at the doctor's. I hope
Yeah.
you're feeling okay.
Feeling fine. Thanks, guys.
Good.
Good.
All right, then take care of yourself, Lou. We'll see you next week.
Bye for now.
See you later. Take care, mate.
Bye.
Shut up.
He said that without moving his lips. Amazing.
Yeah.
Right.
Yeah.
Okay. And then number 3.
Yep. Then there was 3.
Yeah. So there we are. Okay. Right. Well, we're going to move on now to Daz. So Daz, what has been going on? Just let me cue this up for you.
Yeah. Cheers.
Just give me a second, and I will just.
Well, basically, before we actually go into the review of last week, there's been a few events that need to be mentioned that have happened, which basically involves space weather and and all the whole thing and the detection of this, that, and the other. So we'll have a quick run round with that first. All right. Okay then. Thanks, Andy. So basically, the first thing to be mentioned is, of course, after the show last week, we had a quick break, and then we watched the launch of the GOES-U satellite.
Oh yes, and thank you for those of you that watched that with us. It was
it's an amazing event, a beautiful launch. There was some absolutely stunning photography that happened with it and all that. And one of the things that stand in my mind is that when the two side boosters came back and they started their return, to change their direction to come back to the landing zone, is how the exhaust reacted with the exhaust from the original boost takeoff, and it was like two flamenco dancers with the waving of their skirts and things like that. It was absolutely fantastic.
It was beautiful.
And we had spot on landings with some good booms, it's sonic booms.
Yeah.
And then of course later on we didn't stay for it, but we had of course the placement of the satellite in its actual orbit. So I'm jumping ahead a little bit. Let me just go through this. Of course, we didn't know whether it was going to take place to begin with because there was a lot of weather problems, but finally they decided they were going to have a go for it. And it would have been a bit ironic that if weather actually stopped. Go back one. That's it, cheers, Andy. If weather would actually stop a weather satellite. But it lifted off successfully, as we said, from Kennedy Space Center. The Falcon, the SpaceX Falcon Heavy rockets boosted the satellite into geosynchronous transfer orbit. I'm not going to go into too much detail. If you would like more details about the satellite, about what it does, how everything that's about it, because this satellite's not only looking at weather on the Earth. This is why it's in a geosynchronous orbit, which I'll just touch on in a little while why it's there. But it's also going to be looking at space weather. And if you want a bit more detail on the instruments that are on there, then go back, have a look at our live launch, because we discuss it all there, and you'll get a far more in-depth an in-depth view of what we were talking about and what this is all about. So it took off, as I said, in 8 minutes into the liftoff. The two side boosters separated, and they returned to Cape Canaveral Space Station next door to the Kennedy Space Center, touching down literally almost side by side. It was absolutely fantastic. As I said, we had the sonic booms in that. And the imaging during the daytime was absolutely fantastic. So we've got to take that hat off to the people who are actually covering these events now.
Yeah.
So it's gone into a geostationary orbit. It's part of the GOES-R group of satellites. There's only 4 of them. This is the last one. Now, once it was launched, It once it was put into space, it actually became GOES 19. So you won't hear the GOES U anymore. You'll hear GOES 19. And as I said, it was the last one in this series of the GOES R satellites. This will go into as I said, into an orbit, and it's going to actually replace GOES. Now, which one was it? GOES 16, was it?
Yeah, I think so.
It was going to replace GOES 16, and it'll be on what they call the East Station. It'll be looking at the eastern side. It covers mostly the northern United States, but it'll be more looking towards the east. So virtually, you've got almost 360 coverage of the Earth's weather systems, and this is what it's going to be looking at. It's got the equipment on side, the instruments are going to be covering everything: lightning, cloud, hurricanes. They'll even be looking at bushfires, volcanoes, and things like that. As I said, if you want to know a bit more, then go have a look at it. But it'll be replacing GOES 16. There's always 3 satellites. There's one on the west station, one on the east station, and there's one always sat in the middle, and that's a standby. So that if anything happens to any of the other 2, they can immediately move them to the station that's gone down, and then coverage can start. So they'll always have 24 hours, 7 days a week, monthly, yearly coverage. There'll be no gaps. And the instruments on these satellites will give us more and more real-time data. So we'll be able to go get the data, and that will be able to assist emergency services if there's disasters or anything like that. As I said, go and have a look at our original launch program. But as I said, also it'll be looking backwards, and it'll be looking at the sun, and it'll be studying the space weather. And one of the major things on there is got a compact version of a coronagraph. I can't remember what they called it now, but anyway, it's a coronagraph, and the coronagraph, if you remember, is a telescope where they put a disc in the middle, which creates a total eclipse of the sun. So what you're actually looking at when you look through the telescope is the atmosphere of the sun. So anything that happens, we can't normally see it because the sun's too bright itself. It blots it out. It's the same when we have a total eclipse. We can see what's going on in the coronosphere. So this is what they'll be studying. And this, again, is all down to predictions and the study of the actual sun itself, what's going on, so that we can actually make predictions of when we're going to be hit by geomagnetic storms, which can give us problems. Again, as I said, look at our thing. Now, this 4 hours after the launch, this image appeared on the stream, the NASA stream, and it's actually the GEOS 19 as it is now, because it's detached away from the second stage of the Vulcan Heavy, which is that little bit on the right hand side you can actually see by the NASA logo, and now it is actually on its own in space. And what I think is fascinating about this and fantastic is look behind it, there's the Earth, and that is going to be protecting the Earth and the people on Earth with disastrous weather predictions and other disasters as well. As I said, it's going to be detecting volcanoes, hurricanes, and everything. So I just wanted to mention that was on last week, just after our previous show. If you can go to the next slide, Andy. Now, the other amazing little satellite, or probe, should I say, is the Parker Solar Probe. On Sunday, it made its closest pass of the sun since it was actually launched. It actually, let me have a look. It's basically, this is the second to last perihelion, which is when it's its closest approach to the sun. It swept within 5.3 million miles of the sun this time, bringing it ever closer to its final historic close approach of less than 4 million miles, which will happen in the future, which is due in December, actually, of 2024. So that's something else.
Wow.
That's when it'll actually come to its closest. Now, we know this little satellite has been basically what it does is it actually goes into orbit around the sun, and then it fires its engines, goes back out into space, and it will do a loop around Venus. And every time it passes around Venus, it brings it just that little bit closer to the sun. So it's something that's December is going to be its closest. Once it's done all its measurements, then what it'll do is, if dependent upon what fuel is left on there, they will jig it so that it'll actually still be able to give us data for as long as it can actually survive without fuel, because it eventually will run out of fuel. So, as I said, it's the Parker Solar Probe. Mission is solar observation. It was launched on August the 12th, 2018. Operator is NASA. Mission duration is 7 years, so that's until 2025. So it's coming towards its end. Its primary goals are to trace the flow of energy and understand the heating of the solar corona, to explore the structure and the dynamics of the solar wind, to understand what mechanics accelerate and transport energetic particles. And of course, last time it did its last post, we saw some beautiful images of the actual folding of within the actual solar wind, which is something that's been predicted, and they actually found it. And of course, for it to actually do this, it had to have a very special heat shield made, and it was called the Thermal Protection System, which is TPS. It's a revolutionary heat shield made of carbon composite materials. It's 2.4 meters, which is 8 feet in diameter, and 11.43 centimeters, which is 4.5 inches thick. And it's designed to withstand temperatures up to 1,377 degrees centigrade, which is 2,511 degrees Fahrenheit. So again, it's made its class's approach. We will be getting the data back very, very soon, and I'm assuming we will see even greater images than we saw before. And we will, well, I'm looking forward to them. Stunned with it. It's been such a fantastic device. It's providing us with loads and loads of data, and it's going to help us in the future. I think I'll stop it there, because I could go on forever about it, and we don't want to be going there. So if you can move on, Andy, please. Right, the Sun review for the 25th of the 6th, 24 to the 2nd of the 7th, 24. Well, not a lot really happened as regards major events on the Sun. But one thing that did happen is on Friday, if you can move on one, Andy. On Friday, this happened. And as you can see, we had quite a major storm hit us. It didn't last that long. The whole event did last virtually it was from 2 o'clock in the morning, and it did carry on after this for a little while. So it was almost all day. But you could see it building up, then it was dropping down, building up again, and then it's about, what was it? So that's 14. About 3 o'clock, bang, we had that big red spike. That was a KP4, if I remember right. A K4, not KP, a KP4 solar storm that hit us. Now this, if you remember, if you can move on, Andy, if you can remember, at the end of last week's review of the Sun, I showed you this image, and it's of a filament lifting off on the western limb, and it was absolutely huge. It went from almost top to the bottom around the side of the actual Sun, and it lifted off, but it was gentle. There was nothing to sort of like be concerned about. So we said, well, that's not going to be much. And even I thought that after looking at it, and even on the coronagraph, which we'll see in a minute, it didn't seem to be that much of a thing. We thought, well, it's not traveling that big. It doesn't seem to have thrown up much in the way of magnetism, so we're not going to get a big geomagnetic storm. But lo and behold, on the Saturday, it arrived well early, because it wasn't supposed to happen until the Saturday, late or very late Friday, but more Saturday. And it hit us, and it was no good for us in Europe because it was daytime, so we couldn't see anything. Yeah, it traveled to us a lot faster than we were expecting. So that took us by surprise. And this just goes to show, as I've keep saying before, it's very, very hard to judge these things, because if there's other events going on, which there was, if you remember, at the end of the last week, and it's the same as the end of this week, as things go on, things get lost. They get you have to go back and really study all the different events in different wavelengths to see if you can pick up what's going on. But even they didn't pick up that this was traveling a lot faster, and it did create a very small what do you call it, EMP, electrical magnetic pulse, but not big enough to actually cause any damage. And this is why all of a sudden it spiked as it did. It was the actual speed of the event rather than what was actually inside it, and that's why it didn't last that long. So if you move on again, Andy. So here we are. This is our 100 seconds. I've started it early, so you'll see that filament lift off on the right hand side again. It'll go any second now. You'll see there it goes, and it literally sweeps all of it away. When you're in the closer image, you can see it appears that a lot of it fell back to into the sun, but of course it didn't. A lot of it was ejected out into the interplanetary medium. Now on the bottom right, you can see bottom left. Sorry, on the bottom left, you can see a big region coming in to view now. Now that was our old friend. It was 3664 in old money. It then became 3697. And this time it became 3723. And we were expecting quite big things of this, because as it came round, it was firing off big flares and all that. But if you watch it slowly, you can also see other events going on. There's the occasional flare. There's lots of filaments lifting off. But none of these are very big. None of these flares are very big. They're all C's and M's. There's nothing that really massive that's going to actually give us any fun and games. But if you watch the big region that's now just in the center at the bottom, it actually seems to be separating. And this is what happened. It actually broke up, and it lost some of its magnetic activity inside of it. So it's been a bit of a poor performer. In the end, it ended up being 3 separate regions. And right at the end there, I don't know if you just called it in the south, there was that big ejection there. So if you'd like to move on, Andy, here's the coronagraph. There's not a lot to write home. That's that big lift off. So it didn't seem to be moving that fast. Of course, this is a bit speeded up. You'll see other small events come off, but not until very the end will you actually see anything come off, and that's the one at the bottom. So we'll just watch this go through, but you'll see that there's no halos coming towards us. Didn't appear to be a lot happening also on the far side. Well, of course, there was, when last week we had quite a blank area on the sun, and that's now around the far side. So it's just coming around now. You can see these odd events going off, and then at the end you'll see the ejection towards the bottom right, which is that lift off of a filament plus probably a CME. So we'll just watch this run through. It's just going to come now. You can just see the little flag come up in the orb in the center. So yeah, it's as I said, not a lot's actually happened, but all this stuff that has happened has kept our magnetic field, our magnetosphere that's been keeping us safe. It's been keeping it active. It's been kept it ringing. It's on, off, on, off, on, off, because all these little events, they will have an effect in the solar wind, and they will rattle our magnetic field, our protection. So have we finished now? No, not quite. It's a long 100 seconds. There you go. That's the beginning of the last thing. Now this, I wanted just to show you this, because this is a, what was it, the 29th? All of these active regions, you can see is 3732. And this is before it actually really started to break up. 3728 was part of it. Sorry, 3723. was the actual main region, but now it's all broken up, and you've got all these. There's another 3 regions that were part of it that have all become of it. So it's broken up. It's lost most of its magnetic force, and that's why it was a disappointment. But look at this sun on the right-hand side. It's absolutely gorgeous. All that activity in the southern hemisphere. And it wasn't that long ago we had all the activity in the northern hemisphere. And if you can remember, I did tell you that the north and south, even though it's the same sun, they're not really connected in what the action is going on. And this is why we tend to see double peaks. One hemisphere can peak before the other hemisphere. So you get a peak, it will drop down again, and then the southern hemisphere could peak, and then it would come back down again. Now, if you just move on, Andy, I'm not sure which one's next. This is just the last couple of hours, couple of days. And you can see all these little flares going off. There's been quite a few of them. There's a few filaments lifting off, but all this stuff will keep our atmosphere, our magnetosphere, sort of like rattling. It'll keep it unstable. And there is possibly predictions that this can go on until about the 3rd or the 4th, with possibly maybe some storms coming round about, I think, about the 3rd or 4th. Excuse me. And we may just chance, if it is a big one, takes us by surprise, there could be aurora. Now, if you notice that Lee had an aurora on the 28th, and that takes me back to that surprise, CME aurora we had. So for Lee to be able to catch that, he was very, very lucky, and it just goes to show that it managed to get dark enough for him to be able to take it. Here it's no good because we got clouded out again, but it did hang on towards the towards the darkness and that. So yeah, once this is finished, we can just move on, Andy. The count is in. This is what happened last month, and if you look at the far end towards the right, it's dropped. It's dropped a little bit. Now, I have seen that there's some speculation. Oh, is this the peak? The truth is, we will not know for 2 or 3 months. This could still be the first peak. We don't know. Until we actually get a few more months under our belt, will we be able to actually say, yes, this is definitely the peak, and we're now in the decline of the sunspots on the actual sun. And just to prove, if you move on one more slide, Andy, this is the last one. If you look at this information, this is the data, daily solar data for the last 30 days. We're looking at the 3rd column, the SESC sunspot number, and that gives you the sunspot numbers for every day. As you see, we did drop down to as few as 95. I think we did actually drop down a little bit more the other day, but this is up to, what date have I got on here? Up to the 1st. So, yeah, this will tell you literally how many sunspots there are on the actual sun's face for every day. Also, it will tell you how much acreage, if you want to know, or area is actually taken up by these sunspots. And this is sort of like a daily radio flux. I think it's just sort of an average of what we're getting actually hidden in the actual solar wind. And if you look over to the right, you've got all your flares that have been detected for that day. They don't usually match up with what's on other reports, because this is a far more detailed report. So I think we'll end it there. So just keep an eye out, look out, listen to your alerts. Hopefully they'll go off at night time, not during the day, because there was a lot of very disillusioned astronomers who saw what happened on Friday and were well miffed.
Well, anyway, thank you very much, Bob Fleming, and we look forward to a similar report next week. Let's hope something more interesting happens.
Who's Bob Fleming?
You don't know Bob Fleming?
No, I don't know Bob Fleming. Michael Fish.
No, Bob Fleming. Look up Bob Fleming Fast Show. And,
okay.
You will find him, and then you'll realise why I called you Bob Fleming. Okay.
Right. Okay.
All right then. So I think that's about it for this evening, viewers. So thank you very much for being with us for another week. We do appreciate it. We're a bit low on numbers tonight, but of course there are lots of people on holiday and away and doing things. And why not?
Yeah.
It's summertime. Well,
There's
not
lots of
in the
events
UK
going
weather.
on. Yeah. There's a lot of astronomy events going on as well, so all over the place.
Yes,
So,
that's true. There are.
people are off and out.
And here in
things.
Spain, the weather is absolutely, well, I won't tell you what the weather's like. It'll only depress you.
No, it's probably terrible. Probably terrible.
No, it's all right, actually. But
Polar
it's still-
bear weather.
it's still remarkably showery. It's not heavy rain; it's just light showers.
Oh,
But
we had a
quite
downpour
frequently,
here.
which for June is really weird weather. We never have showers in June. June is usually a month without any rain. So but it's great. We need the water, so fantastic.
Yeah. We need
Yeah. So
for
there
your
we are.
aquifers. For your aquifers.
Hi, Sandra. Glad you managed to join us. We're just going home. Yeah, thank you. Great timing.
Hello, goodbye.
Yeah. So just in case you haven't seen it, Sandra says she has family over from Australia.
Oh,
so
fair
there we are.
dinkum. Fair dinkum.
Yeah, fair dinkum. Yeah. So they'll be hanging upside down from your ceilings, no doubt. So
They're not possums. They're not possums.
Thank you for being here anyway, Sandra.
Yeah.
It's much appreciated. And we hope you can join us a little more next week, obviously. Gerard, thank you so much for your generosity again. Much appreciated. And we will see you all next week. Not quite sure what we're doing next week, but we will endeavour to line something up for you. What I was thinking, guys, we've been talking a lot about China tonight. I think it might be worth at some point doing a review of exactly what China's doing in space these days, because they are moving on in leaps and bounds. And the fact that Bill Nelson was obviously jealous of the Chinese having the lunar sample when it should have been from NASA, of course, in his view, and then trying to say, well, the Chinese didn't invite us to take part in the research on the sample. It's just I don't know what's going on.
Yeah, but
we also.
Sorry. I was going to
Sorry.
say, of course, we would have had Mars samples back if NASA had been a bit more sensible about where they put the money.
Yeah.
So,
We've got somebody called Pino Clean saying howdy from Australia, and howdy to you too.
Yeah.
Thank you very much for being here. There we are. Mention Australia and they're all partying.
Yeah.
So there we are. Nice to meet you. Hope you can make it next week. I was just going to say one thing before we go. We were talking about the mishaps of the Chinese space program this week, with two very, very dangerous incidents taking place with falling boosters in China. But there was one launch that we all remember that I think is one of our favorite videos here at Space Oddities, because this was a rocket launch that had never been seen before in the history of rocketry. It came from a company called Astra. How long ago was this? 2 or 3 years ago?
About 18 months, 2 years ago. Yeah,
something like that. This came courtesy of a company called Astra, who's since gone bust. You probably see why. So this was a novel attempt to launching a rocket. Instead of firing it vertically into the sky, fire it sideways.
Yeah, how to clear the tower.
Yeah. This is absolutely brilliant. So anyway, I think we need to see that again. Let's just do that again. So hang on, let me just put this back in the middle. Yes, so this actually took off sideways due to a malfunction. It travelled for about half an hour over a field. We always say the farmer got the field ploughed for nothing. And then eventually it managed to pull itself together and rise vertically into the sky. But of course it had used all of its fuel and it couldn't get very far up into the sky, so they destroyed it. But this has to be the funniest space launch in history, the Astra rocket. And it's horizontal launch.
Because it was, as I said before, just after this, as you said, it goes half a mile across this field, ploughing the field for, and sterilising it for him as well.
Of course.
There's, as you can see in the background, there's a slight hill, so they can't be seen from where the long distance camera is. And you could actually, when you see the whole film, you can see the actual cameraman trying to find it. He's sort of like panicking. Oh, there it is, and he moves over, and it's slowly crawling up into the sky. And then they, like you say, they had to self-detonate because it used so much fuel going sideways.
No, there was no way that was going to make orbit after that. No. But that still makes me laugh. And that is one of our favourite videos here.
But the funniest thing is, and this is why one of the reasons I thought it was actually on purpose, because I watched it live, is that it was surrounded by sort of like crash barriers, and the barriers on that side were open. Yes. And I thought that's why they were open, because it was designed to do. I thought that's a novel way of clearing the tower.
Yeah,
and then you suddenly realise when the bloke couldn't find it in his viewfinder, I thought, nah, this isn't right.
Sorry, just before we go one more time, I just got to see this again. Oh, that's so funny.
Yeah, it's struggling to get itself straight and horizontal.
Absolutely. Yeah. Anyway,
vertical again. I mean, sorry.
Anyway, just as a final thing, we just need to get a very, very quick mention to the fact that both Blue Origin and ULA on the same day sued the FAA in a bid to stop SpaceX flying out of Cape Canaveral. And this is just disgraceful behaviour. It's Jeff Bezos, as we know, Jeff Bezos has his lawyer on speed dial, as we know. He's an extremely litigious man. Any criticism, anything you do that he doesn't like, he reaches for his lawyer. But ULA, Tory Bruno, mate, I thought you were better than that. I thought you were above that.
But then one you've got to remember is when you see who ULA are, you can understand why. It's basically Old Spice. It's Old Spice?
Old Spice.
It's Old Spice. Yeah, we're not talking about Rogers Cologne. But
well, by the way, viewers, if you want to know what to buy Daz for Christmas, he's just blurted out that number one thing on his Christmas list is a bottle of Old Spice. So please bear that in mind. So there we are. Anyway, look, I mean, they both know that if SpaceX start operating the Starship out of Cape Canaveral, they're finished, because they would just completely clean up the market. So Blue Origin have come up with a completely specious and inaccurate legal objection to why SpaceX shouldn't be allowed to operate out of Cape Canaveral. Environmental reasons and this reason and that reason. It's so obvious that Bezos never actually read the environmental study that the FAA had prepared. I mean, that's quite obvious. Hadn't read it at all.
Did you see the list of demands that he said that they would have to follow? And it included compensation to any interference to other launch facilities or for launch providers. It's just absolutely, it's a crybaby list. It really is, and it'll be funny to see how this goes. And the thing is, what makes me laugh is you're talking about ULA and you're talking about Blue Origins. As regards new rockets, sorry, Blue Origin. If they ULA and Blue Origins, if they what are they actually doing in new rocket?
Yeah, nothing.
I mean, they're not doing anything. They're still producing expendable rockets. There's no guarantee that they can produce these things on time. We still haven't seen the new. Is it the new Glenn? A full mock. We've seen mock-ups and things like that, but we haven't seen.
Just engineering mock-ups.
Yeah. So at the end of the day, when Mr. Bezos can actually launch something into orbit, which he's never done, then come and talk to us.
Exactly.
You're so far behind the times, and you've got nothing to shout about. So you can't back. But also, if he's going to sue the FAA, he's going to be wanting them to issue licenses on time for him. Oh, wonder how that'll go.
Yeah, exactly. Anyway, it's not going to get anywhere. So but the fact that ULA and Blue Origin did it on the same day, independently of one another.
Yeah, of course they did. Yeah.
All right then, Biz, we'll leave you alone. Promise. So we'll see you next week. Thank you for being here. Thank you for your generosity. Do keep an eye on the channel. Do keep an eye on the Facebook page. Thank you for the coffees this evening. I've noticed that we've had. Thank you so much for everything. And as usual, we'll see you back here on Tuesday next week. And that's it, really. Have a fantastic week. Be good to each other. Take care. And
thanks for joining us.
Thanks for joining us.
Take care.